Hey guys, and welcome to another video of my A-level physics revision series. In this video we're going to be starting the section on current and electricity. In this video we're going to be doing current, potential difference and resistance, and this is the start of the electronics section. So what is electronics? What is electricity? Well, electricity, what would you think of when you think of electricity? Well, you'd sort of think of like a battery or something. So obviously you've got like a battery, and you describe a battery as kind of like a source of electricity. We'll come on to what exactly that means, but when a source of electricity a little bit later. But you know, you've got things like a battery, connected to a battery. You've probably got things like a light bulb. I think this is the symbol for a light bulb. I should know, shouldn't I? But I kind of have forgotten. You know, doing university physics, you do forget the basics, unfortunately. And then, you know, you might have this might give off some light. Well, I mean, you'd hope so if it was a light bulb. It'd be a bit of a shit light bulb if it didn't. And you've got, like, say, a resistor here, and a resistor doesn't really do much. It just sort of moderates the flow of current through the circuit here. So you see, electricity always flows in a circuit, which is probably something you remember from GCSE. But what exactly is electricity? Well, electricity, if we go back to our kind of model of what a metal is, so let's draw out what a metal is. The structure of a metal, it's like a crystal structure in which you have the nuclei of the atoms in kind of like a crystal lattice. It's called a crystal lattice, this thing. And of course they're ions, they're positively charged. They've actually lost their valence electrons. And where these valence electrons have gone, well, they haven't gone too far. They haven't actually left the metal, but they're said to be delocalized. So they're kind of just swimming about in this, you know, sea of electrons in a metal. So you've got all these delocalized electrons, and the point is that they're not bound to the atom, and therefore, because they're not bound to the atom, they are actually able to move throughout the metal itself. And this is called a current. A current is simply the movement of electrons through a metal. In fact, to be a bit more specific, it's the movement of charge through a metal. Of course, electrons carry a negative charge of 1.6 times 10 to the minus 19 coulombs, which is a very small amount of charge. But you've got to remember, of course, there's billions and billions of electrons moving through the metal. So overall, you're going to have quite a strong effect. So you can think of it as a bit like water flowing through a pipe. So say you've got a pipe here, and you've got sort of a flow of water that's coming through. And you can think of, you know, obviously we have water currents, and likewise we have electrical currents. And the amount of water that flows depends on what's called the flow rate and the time taken. But if more water's flowing in any given time, then you say it's got a higher current. And the mathematical definition of current, which we give the symbol I, is the charge divided by the time. Or we can otherwise write it as the charge passing a particular point per unit time. So say you take this point here on this tube, you wait 1 second. The amount of charge that passes this point right here along this sort of wire is the current. And current we give the unit of amps. And of course charge we give the unit of coulombs, and time we have the unit of seconds. So you can very easily say that 1 amp is simply equal to 1 coulomb per second. And the way you measure current in a circuit is using an ammeter, and that's normally given this electrical symbol right here. And the key thing is you always put the ammeter in what's called in series along with other components. And we'll go through that in a bit more detail and why it is that way in a later video. So the next key thing about electricity is this thing called potential difference. And potential difference is always a very odd thing because you can't really sort of see it or visualize it, but the best way to think of it is the energy per unit charge. And basically the thing is about potential difference is that to make electric charge flow, to drive a current, you need to do some work on it. You know, you're going to need to put in some work in order to get the electrons around in the circuit. And the potential difference mathematically is defined as the work done per unit charge. So the potential difference V right here is defined as the amount of work you need to do on the charge, which in this case is of course an electron, divided by the charge of the electron. And if you think of it, if you go back to the water analogy, the potential difference is a little bit like the pressure that's forcing the water through the pipe. If I draw a horizontal pipe, what's going to cause that water to flow? The only thing that's going to cause it is a pressure gradient along the tube. And you can think of voltage as a bit like a pressure gradient, which is driving the current to flow, driving the electrical current to flow through the circuit. And so therefore we can write a more formal definition of potential difference as this. The potential difference across a component is 1 volt when you convert 1 joule of energy moving 1 coulomb of charge through the component. So that is our definition of the volt right here, which is of course the unit for potential difference. Potential difference is measured in volts. You might sometimes hear it called the voltage as well, but voltage, potential difference, exactly the same thing. It's the work done per unit charge. So we can also write that 1 volt is 1 joule per coulomb. So that's potential difference. So how are we going to link these two things, the current and the potential difference, together? And I'm sure you guys probably already know the answer. But basically, if you put a potential difference across the circuit, you'll of course get a current to flow. But how much current you get for a particular potential difference depends on what's called the resistance of the component. Now, the resistance is a quantity that is specific to any electrical component. Say it's a bulb or a light emitting diode or a motor or anything like that. Anything has a resistance. And the definition of resistance is the voltage divided by the current. And this is a very important relation. It's called Ohm's law. And this quantity right here, this R, is known as the resistance, which has units of ohms right here. And normally we give the symbol for the unit of ohms, this omega symbol right here. And this equation basically defines what resistance is. So resistance is the ratio of the potential difference across a component divided by the current flowing through that component. And you can think of resistance basically as a measure of how difficult it can be to get current to flow. You know, obviously the greater the resistance, you're going to have less current. If you simply rearrange this relation, V equals IR, therefore if you have a constant potential difference being driven across the circuit, then if you increase the current, then you will of course decrease the resistance. And also the opposite's true. If you say you decrease the current, or say you increase the resistance rather, it's probably more likely that, you know, if you increase the resistance, that's kind of the causal variable, then you're going to get a much lower current. So the amount of current you get is basically down to the resistance properties, you know, and that's a material property, which then leads on to having a certain current flowing through the circuit. Now this relation V equals IR kind of implies that this R is a constant right here. I did say it was a constant for any material. However, this is not generally true, but it's true. This relation right here is true for an ohmic conductor. So for an ohmic conductor, the current you get is proportional to the voltage. If you simply rearrange this equation, you simply get that I equals V over R, and therefore the constant of proportionality is simply 1 over R. So the current is proportional to the voltage, with the constant of proportionality being 1 over R. And basically, provided the temperature is constant, the current through an ohmic conductor is directly proportional to the potential difference. But of course, this resistance right here, this will change if the temperature changes. Normally, I think if the temperature rises, then you're going to get much more resistance, because of course, if you think about what temperature is, it's lots of little, vibrations of atoms within the metal. And therefore, the electrons are going to find it much harder to get through if they're getting bumped about a bit more. Whereas if the temperature is lower, then the electrons will get through, and therefore the resistance will be a lot lower. And you can actually graph this relation right here. So you can plot a graph, and what I'm going to plot is current along the y-axis, which is of course measured in amps, and potential difference along the x-axis, which is of course measured in volts. And I said that for an ohmic conductor, the current is proportional to the voltage, and so therefore you're simply going to get a straight line, a linear relation between the current and the voltage. So say for a given circuit, you put 2 volts across it, and then you get a current of 0.5 amps. For example, if you put 4 volts, or if you put 4 volts across it, then you can expect to get 1 amp. It's proportional. So the ratio of current and voltage is always the same, and the current divided by the voltage is of course the gradient, which is 1 over the resistance. You've got to be a little bit careful. It's not the resistance, it's 1 over the resistance. Of course, if you were to plot it the other way around, voltage against current, then of course you would have the resistance. But in this case, the gradient of our graph right here, which is the ratio of the y-axis to the x-axis, is 1 divided by the resistance. But the key thing is that this is a special case. This is in fact a special case. Ohmic conductors are kind of like an idealized situation. Not all conductors behave like this, and indeed as we go on we'll see that there are some conductors that have very different current voltage graphs. The name of this kind of graph is simply called a characteristic IV. It's called IV simply because you've got I, which is current, and V, which is voltage. But every component has a characteristic graph, which we will see in a moment. So let's plot some of these graphs, and this time I'm going to draw, rather than just the positive axis, I'm actually going to draw the negative axis as well. So here's our current axis, and here's our voltage. Here's the 0 point, and I'm going to just redraw the graph for a metallic conductor. And we said that this metallic conductor obeyed Ohm's law, and so therefore we got a straight line. And of course, if you apply a negative potential difference, you're going to get current flowing in the opposite direction. It's still going to be proportional, so you're going to get a graph that looks exactly like this. So that is the case for a metallic conductor. But what about our next component, which is going to be for a bulb, a light bulb? Is a light bulb going to obey the same relation as the metallic conductor? And the answer is no, it doesn't. The light bulb, in fact, has a different curve than the simple metallic conductor. In fact, it does something a bit like this. It's shaped a little bit like this. I'm just drawing my axes. And as you can see, the current is not proportional to the voltage. In fact, the current obeys a rather weird relation to the voltage. It starts off looking like it's going to be proportional around this point here, but then at higher voltages you can see that the increasing the voltage up at this point here, increasing the voltage has no further effect on increasing the current. And so therefore you can conclude that the bulb is not an ohmic conductor, and therefore it doesn't obey Ohm's law. Probably more the other way around. It doesn't obey Ohm's law. I is not proportional to V, and therefore it's not an ohmic conductor. And the reason because of this is because the current flowing through the lamp increases its temperature, and therefore the resistance of the metal increases as the temperature increases. And that's true of this bulb right here. Whereas for the metallic conductor, we assume the temperature was constant, and therefore you're going to get this nice straight line. But with the bulb, obviously, if you apply a large potential difference, then you're going to get much more resistance, which is going to have an effect on the current. So those are the two simple cases for metals. However, I'm now going to introduce a new type of material, and this type of material is called a semiconductor. Now, what is a semiconductor? Obviously, you've heard of conductors, which of course conduct electricity, and insulators, which don't conduct electricity. Well, semiconductors is a bit of a sort of split between the two. It's a bit of a compromise. Semiconductors have nowhere near as many charge carriers available. So if I draw out a semiconductor diagram, then of course you're going to have this crystal lattice as before. However, the number of charge carriers available is nowhere near as much as a metal. However, if you change the temperature of the semiconductor, if you supply some energy to it, then more charge carriers can be released. It's actually very complicated how it works, but if you apply some sort of energy to it, then you basically can increase the amount of valence electrons, and therefore you can increase the amount of current flowing. And therefore this means that they make excellent sensors for detecting changes in their environment. And you need to know a few different applications of semiconductors, 3 in particular. You need to know about thermistors. I'll write them down. You need to know about what thermistors do. There is a bit of a clue in the name, being thermal. You can tell it's got something to do with temperature. LDRs, which stand for light-dependent resistors, and diodes. Of course, you've heard of light-emitting diodes probably. So let's start out with the thermistor. So what is a thermistor exactly? Well, this is a thermistor. This is the symbol for it. It's kind of like a resistor, except it's got kind of a weird line through the middle of it. And basically, a thermistor changes its resistance. I'll write this down. It changes its resistance due to the temperature. And what that means is that if the temperature changes, the actual value of the resistance actually changes itself. But the type of thermistor that you need to know is actually called an NTC thermistor. Now, what the bloody hell does NTC stand for, I wonder? Well, NTC stands for negative temperature coefficient. And what this means is that the resistance actually decreases as the temperature goes up, which is a little bit counterintuitive because, of course, I said in the case of the light bulb, obviously the resistance increased if the temperature went up. But in this case, with this weird resistor right here, this thermistor, the resistance actually decreases as the temperature goes up. So if we sort of plot a kind of a graph of temperature, which is in degrees C, against resistance R, then we sort of get a relation that looks a little bit like that. So you can see that if the resistance does intercept the axis right there, if the temperature increases, the resistance actually decreases. And this leads to a graph which is similar to the one for the bulb, except it kind of does this right here. If you remember with the bulb it sort of rose sharply to begin with and then sort of flattened off, whereas with the thermistor it sort of starts off very slow but then gradually increases for higher voltages. So that's a thermistor. Basically, increasing the current through the thermistor increases its temperature, And the increasing gradient of this characteristic graph tells you that the resistance is decreasing. So for higher temperatures, the resistance is decreasing, and therefore you're going to get a sharper gradient right here. So that is the thermistor. The next one is the LDR, or the light dependent resistor. Similarly for the thermistor, it's almost exactly the same, except instead of temperature along the bottom, you're going to have something like light intensity. The intensity of light can be measured in various manners. Let's go with lux. It's just a unit for light intensity. And we're going to plot that against resistance like before. And exactly the same as the temperature, we're going to get a graph that goes like that. It's going to decrease for greater light intensity. So the higher the light intensity, the lower the resistance. And the symbol for a light dependent resistor is this right here. It's like a resistor, except it's got a little circle around it, and it's got two arrows here, and the two arrows of course represent the light coming in. And so you're going to get a very similar looking IV graph as for the thermistor. For low voltages it's going to sort of be quite shallow as the resistance is lower, but then for high voltages it will sort of gradually start to increase, and it's of course going to be symmetrical about the 0 point. So that is LDRs. And the last of the three components which use semiconductors are diodes. Now diodes are a little bit different to the other two. The other two are just sort of environmentally dependent resistors, whereas the diodes, the whole point of diodes is that they only let current flow in one direction. That is the whole point of a diode, is that it only allows current to flow in one direction. Now you don't need to know how a diode works. It's very complicated and requires a bit of knowledge on semiconductors. But this is the symbol for a diode, and also you can have, of course, LEDs, which stands for light emitting diodes, which is probably the one you're a bit more familiar with, and you can just simply represent that as a bit of light coming out of the diode. So that is for an LED. This is just for an ordinary non-light emitting diode right there. So what does this current voltage curve look like for an LED or a diode exactly? Well, let's draw our axes as usual. So what do we expect to get? Well, we're not going to get very much if the current's flowing through in the other direction. You might still get a little bit due to imperfections, but you're going to get absolutely not very much, hardly at all, flowing in the opposite directions. However, at a certain point right here, you will suddenly get a big rise, like so. You'll suddenly get a very, very sharp and rapid rise. And this threshold point is about 0.6 volts. It's slightly different for every type of material that you choose. But if you apply a positive potential difference that's greater than 0.6 volts, you will get a rapid rise in current flow. And this basically does reflect the point of what a diode does. If a potential difference is applied in the right direction, so if you're on this end of the graph right here, then you'll get a current flowing in one direction. Whereas if it's not applied in the right direction, if you're on this end of the graph right here, then you'll get very, very little flowing. So therefore, this graph verifies the point of a diode. And there's actually a term called bias, which basically refers to which direction the current is flowing in. If you've got a forward bias, then the diode will conduct. If it's in this zone here, if it's past 0.6 volts or above, then you're going to have conduction. If you have no bias, then of course it's not going to do anything. That just basically means there's no voltage, so you're going to get nothing. And if you've got reverse bias, then you will also get nothing as well. So you don't need to understand how this works exactly. It is very complicated, but that is basically what a diode does. And I think that's probably about it for this video. I've covered quite a lot in this video, and so I'll see you guys in the next video.